We're going to begin to interpret derivatives now. We're going to start with a ball is thrown vertically upward with a velocity of 80 feet per second, and its height after t seconds is s equals 80t minus 16t squared. We're asked to find the maximum height reached by the ball and then the velocity when the ball is 96 feet above the ground on its way up and then on its way down. Now I went ahead and got the graph of y equals 80x minus 16x squared, and what we can see here is that anything below the x-axis doesn't have any physical meaning, but at time t equals 0, the ball is thrown up, and then we hit our maximum of 100 feet high, and then we come back down and then hit the ground, right? So what we're asked for is the maximum height reached by the ball. We can see here that it's 100, but that's, I mean, the answer isn't the point of this, it's the process. And I hope you're thinking about derivatives and tangent lines because, you know, well, that's what we've been doing. And you can see that at the maximum, the tangent line is horizontal. And I guess that should really be about right there. And for this horizontal tangent line, we know that the slope is equal to 0. So what we need to do is find where s prime is equal to 0. This is for part A. S prime is equal to 80 minus 32t. And so if s prime is going to equal 0, then that means that t is equal to 80 over 32. Divide out the, I guess, 16s. So t is going to be 5 halves, or 2.5 seconds. We're not done because we were actually asked for the maximum height, not when it reaches it. But notice that what I didn't do. What I didn't do is find s prime and then set that equal to 0. That would be implying that s prime is always 0, and that's just not true. Just wanted to make that point. What we need is s evaluated at t is equal to, I'll use the fraction, 5 halves. And that's going to be 80 times 5 halves minus 16 times 5 halves squared. 2 into 80 is 40. 40 times 5 is 200 minus, this now becomes 25 over 4, as you see, right? So this is going to be 4 divides into 16 4 times. 4 times 25, 100. Of course, s is equal to 100 feet. We knew that from the picture, but now you know how to find it. Part B is a little more interesting. What's the velocity of the ball when it's 96 feet above the ground on its way up and on its way down? 96 feet is somewhere around, let's see, here. And what we see is we cross 96 feet and the ball is on its way up, and we cross 96 feet and the ball is on its way down. What we need to do then is we need to, for part B, find the time such that the height is 96 feet. Then find for the velocity s prime at those t values. I'd like for you to go ahead and do that and then come back when you're done. The equation we're solving is 96 equals 80t minus 16t squared. Getting everything on one side set equal to 0, dividing by 16, factoring, and then solving gives us that t is equal to 2 or 3. That means that when t is 2 seconds, we're at 96 feet. When t is 3 seconds, we're at 96 feet. And then s prime is going to give me the velocity, right? So s prime evaluated at t equals 2 is equal to 16. At t equals 3 is negative 16. That should make sense. 16 feet per second on its way up, negative 16 feet per second on its way down. That implies that up is positive and down is negative. To wrap this up, we're going to say that the velocity is 16 feet per second on its way up and negative 16 feet per second on the way down. You know, I blew right past how the derivative of position is velocity. We talked about it in a previous video, but I'm just going to take a moment here. We used s prime. in part A and part B way down here, right? And remember that with these symbols here, S prime is equal to ds dt. That is change in position over time. That is how we get velocity. Now with that in mind, we're going to move on to the next exercise here. A tank holds 5,000 gallons of water, and we've got water draining from the bottom of the tank, and it takes 40 minutes. We have a function that gives the volume V of water remaining after t minutes as V equals 5,000 times the quantity of 1 minus 1 over 40t squared. And that's good for t going from 0 to 40 because at 40 minutes the tank is empty. We're asked for the rate at which the water is draining from the tank. And a moment ago, we just said that S prime was ds dt for the position function, right? That was how position was changing over time. What we're looking at here, I'm going to change the color because I don't want us to try to connect that too much with what I have in blue. What we're looking at here, though, is the rate at which water is draining. We can think of that as the rate at which volume is changing. And in terms of calculus, that is how volume is changing over time, or dv dt, which we could also call v prime. So our steps here are going to be find dv dt when t is 5 minutes, 10 minutes, 20 minutes, and 40 minutes. And then we're going to think about at what time is the water flowing out fastest, when is it the slowest, and summarize your findings. We'll get to all of that. What I want you to do is find dv dt, also known as v prime, for this function, and then go ahead and evaluate it at 5 minutes, 10 minutes, 20 minutes, and 40 minutes. A word that I want to make, though, is you're going to use the power rule. Folks, don't forget the chain rule. Come back when you're done. For the derivative, I use the power rule. 2 times 5,000 is 10,000. And then we have times 1 minus 1 over 40t. And then the chain rule, the derivative of 1 minus 1 over 40t is negative 1 over 40. And I simplified, so we have that dv dt is equal to negative 250 times the quantity of 1 minus 1 over 40t. Because we're evaluating this, this is a good form for the derivative, and all I need to do is plug in 5 in place of t to find out the rate that it's draining at 5 minutes. And I see that that's negative 218.75 gallons per minute. And then as we move on, I just substituted 10, 20, and 40 in turn in place of t to get 187.5 gallons per minute. Oh, negative. It's draining. Negative 125 gallons per minute and 0 gallons per minute at 40 minutes. It is empty. Clearly, this is draining the fastest when the tank is full, and it's draining the slowest when it's empty. And to summarize the results, we can say it starts draining quickly and then slows down as it empties completely. You may have experienced this if you've ever been somewhere that has a big old thing of coffee or tea or something, and when it's full, it fills your cup up really fast, and when it's not so full, it can take forever to get your cup full. Well, Torricelli here is the one who figured this out, and this is the calculus that tells you what's going on. For good form, I'm going to go ahead and box all of my answers. There's the summary, A, B, C, and D. And notice I'm including the units gallons per minute because it's good to do in a real world situation. Also, sometimes knowing what dv dt and gallons per minute, like sometimes thinking about gallons per minute can help us think about dv dt. And we'll see that probably more in the next series of videos, but here it is demonstrating good form.